Hey, cutie. Hello again, astronauts. Today we will be interviewing Rebecca Deasing. Rebecca Deasing is a PhD candidate studying theoretical astrophysics, specifically high-energy astrophysics, at the University of Chicago. She uses computer modeling to understand the mechanism responsible for cosmic ray acceleration due to shocks like supernovae. In her spare time, she enjoys hiking, running, camping, watching Star Trek, and snuggling with her puppy. Her physics deals with the hottest, most violent explosions in space. Think supernovae, active galactic nuclei, that time Janeway took out the Borg Queen's transwarp hub. Very hot, lots of radiation, much violence. Things are ionized. Hey Rebecca, thank you so much for agreeing to this interview. After months of asking, reminder messages, schedule changes. It's cool, you're super pretty. I mean busy, you're super busy.
Thanks for having me, Astra.
So let's start with the basics. What are cosmic rays?
So cosmic rays are energetic particles.
Wait, so they're not rays?
No. That's, unfortunately, astrophysics is full of misnomers. It's a historical thing. We have this habit where something gets named by a person who doesn't really know what the thing is, and then the name sticks, and then we figure out what the thing actually is. So cosmic rays aren't rays, they're particles, but we're too lazy to change because everyone's using cosmic rays.
Okay, so I'm just going to pet my miniature dragon and ask you to continue defining cosmic rays.
Okay. Anyway, cosmic rays are energetic particles, so mostly protons, atomic nuclei, and electrons. And these are the most energetic particles that we know of in the universe. So the goal of my research is in large part to understand where these particles come from, how they're accelerated, and so on and so forth.
So small things, lots of energy, not rays.
Yes. So one thing you can think of energetic particles on Earth that we generate in experiments. So if you've heard of the Large Hadron Collider at CERN, there you get very energetic particles. These are human accelerated using a system of magnets. You can do the same thing with astrophysical objects in space. So this just happens naturally, and we're trying to understand the processes responsible for accelerating these particles.
So, you're gorgeous, smart, funny, accomplished, well-spoken.
Thank you.
Did I already say gorgeous? Anyways, I forgot my next question. What's it like being so amazing?
Well, sometimes people get really creepy around you, and it's a little awkward, gotta say.
Yeah, I can imagine that happening in another situation that isn't this one.
Definitely not this one.
Yeah, thanks.
Not awkward at all.
Definitely not awkward. So... So, you study cosmic ray acceleration, the making of the things going very fast.
Yes.
Why?
So the idea behind my research, and more broadly speaking, high-energy astrophysics, is to understand some of the most extreme environments in the universe. So you can think of a lot of astrophysical objects, in my view, as giant laboratories. So if I've mentioned the Large Hadron Collider on Earth. This is a place where we can probe extreme environments in, kind of a very small scale. But sometimes you want to probe really energetic, really hot environments, basically pushing the boundaries of physics as we've been able to test it. But you can't always do that on Earth, so you are limited.
Are you saying that size matters? The size of the Earth is just too small for you?
Yes. So I like my explosions to be bigger. In particular, I'm interested in supernova remnants, which is what's left over after a star explodes.
Okay, that's very big.
Yes.
That is quite big.
Yes, it's very, very big. Much larger than anything we can achieve on Earth. The idea here is to push the bounds of the physics that we know by looking at regimes that have really extreme magnetic fields. You have a lot of energy available to make things happen. And you are therefore dealing with particles that are completely ionized, so we call this plasma. When all of the electrons have been separated from protons, you don't have any neutral atomic nuclei. Physics gets a little weird in these environments, and so we want to understand that. The idea here is that these astrophysical objects, you mentioned active galactic nuclei, supernova remnants, these are places to test, and the way that we can test is we make theoretical predictions about how things like, say, particle acceleration should work. And those predictions lead to expectations about the light we should see from these things. And then we try to see if the light coming from, say, a supernova remnant agrees with the light that we predict.
So supernovae are basically your giant laboratories. So you study how supernovae accelerate cosmic rays because the Large Hadron Collider is just too small for you.
Yeah, basically. And actually, I'm not limited to supernova remnants either. That's my main go-to laboratory, but active galactic nuclei and other energetic phenomena in the universe, so winds that are produced by stars, all of that, are also laboratories that I make use of in my research.
Are there any real-world applications to anything you do? Any near-term benefits to humanity?
No, probably not. So what I do is what would be considered basic science. So this is a lot of fundamental research where you're trying to understand, for example, the laws of physics as a whole, that sort of thing. All of that research sometimes does have payoffs and has real-world practical applications, but the real goal is furthering human knowledge and furthering our understanding of physics, which often does end up having some benefits and can translate into technological advances, but that isn't the goal of my research. It's really to improve humanity's understanding of the cosmos.
So to follow up on your research having no real-world applications, would you say that the real world and humanity are overrated and escaping into theoretical computer models of faraway space explosions is truly the only rational response to the dismal reality we're surrounded by every day?
Honestly, sometimes that's true, yeah.
Let's focus on supernovae because that was your most recent paper.
Yes.
I'm not stalking your papers or anything. I just, I hear things. So anyway.
Can you cite me, please?
Sure. The next time I publish a scientific paper, I will cite all of your papers.
Thank you. Gotta keep that H factor up.
So you study cosmic ray acceleration by supernovae. Now, I get that a supernova is a giant space explosion and cosmic rays are small things going really fast. So I understand big boom in space makes small thing go fast. I got there. But I'm assuming that this is slightly more complicated than just the same mechanism that makes shrapnel go out of a grenade. So how do supernovae accelerate cosmic rays?
So the part of a supernova that's actually responsible for accelerating particles is something that we call the forward shock. So a shock in physics is something that you get anytime that you have anything moving faster than the speed of sound.
Wait, I thought that in the vacuum of space there is no sound, because, it's a vacuum.
So in a true vacuum, there is no sound. That's true. But space isn't completely a vacuum. In fact, there is a very small amount of particles floating around in between stars. We call this the interstellar medium.
Wait, because it's a medium and it's interstellar. Wait, is there something in astrophysics that has the right name?
Yeah, names in astrophysics are either really bad or really boring.
Oh.
In that sort of environment, a typical density that you might see is 1 particle per cubic centimeter. So that's 1 proton, which is not a lot, in a cubic centimeter, so something, yay big. When you talk about cosmic rays, they are approximately 1% of those particles, and the most energetic ones tend to constitute an even smaller fraction of those cosmic rays. Sometimes refer to cosmic rays as the 1%, since they do carry most of the energy in... Yeah, anyway.
Why don't you leave the jokes to me?
Fine.
So, shock waves travel through this interstellar medium faster than the speed of sound. Why does that accelerate cosmic rays?
So when you have a shock, you end up with a discontinuity. Essentially, what happens is you have a region in front of the shock, the kind of unshocked medium, that's much cooler, much lower density, and then the shock itself, this thing that's propagating outward, will heat that medium and compress it. So right behind, you have this different medium that is much denser, much hotter. And so fun things happen when you have a discontinuity. And so in particular, if you have some regular old particle from the ISM, and it is kind of moving around, and these particles actually get scattered pretty frequently. So what that means is the particle hits something else and moves off in another direction. In this case, the thing that does that is actually magnetic fields. Whenever you have a kink in your magnetic field, you get a little bit of a scattering. And so you can think of these particles as taking this sort of random walk around the shock.
Oh,
right?
Like what Cece does.
Exactly.
Okay.
Yes.
So they're little CCs.
Yep. Kind of walk, hit a magnetic perturbation.
Or
walk
a wall.
in this direction. Or a wall. Exactly. And actually, we sometimes refer to these as magnetic walls. And you get scattered. And so this is how you're moving around, right? Now, it just so happens that whether you gain or lose energy every time you kind of hit a wall depends on how you hit it. So you can think of the cosmic ray as a tennis ball, and the magnetic wall or the magnetic perturbation is the tennis racket. Now, if you want to make the cosmic ray go faster, you want to hit that thing head on, right? You want to swing your tennis racket at the ball so that it has a head-on collision, right?
Yeah.
Now, if you want to slow it down, you could basically try to, say, catch that ball on your racket. So that would be what we call a tail-on collision. Basically, you're moving in the same direction as the tennis ball to try to slow it down. Obviously, catching a tennis ball on a racket would be really hard.
Maybe we could change the metaphor and make it catching it with a baseball mitt.
Exactly. Although what matters is the way that you move it.
Okay. Well,
So-
when you catch a baseball with a baseball mitt, you don't just hold your hand out. You bring it back a little.
Apparently that's how sports ball works. Good to know.
You're almost the perfect woman. So close.
I don't do sports. At least not ones with spheres. We know that a head-on collision gives you energy, but a tail-on collision removes energy. So if you could preferentially get head-on collisions, that would mean that you would gain a lot of energy, right? So the idea behind this process is you have these particles that are, moving around, and say you are a particle that is sitting in front of the shock. So this is unshocked, regular old interstellar medium, and now this shock is coming at you. It slams into you head on, and guess what? As you cross, you gain energy. Now you're behind the shock. And at first, this is new, you're behind the shock, what's going on? But you're gonna keep doing your little diffusing around, making your random walk, and suddenly, behind the shock is gonna feel like home to you. So now, what happens if you accidentally cross the shock the other way, going from behind the shock to in front of it? Well, it turns out that from your perspective, now that your frame of reference is the area behind the shock, the stuff in front of the shock actually looks like it's coming at you. And so what that means is you're going to get another head-on collision. And so every single time a particle crosses this shock, it gets an energy gain. It's almost like it's getting ping-ponged back and forth across the shock.
But it only works because between the ping pongs, it's hitting a bunch of other stuff and starting to feel at home. So
Exactly.
it doesn't feel like it's being ping ponged. It feels like every once in a while it gets smacked for no reason.
Exactly. And so in this way, you can give a particle a ton of energy. And so we call this process diffusive shock acceleration. So the idea is the particle is diffusing, that's what we call that random walk. There's a shock, and it accelerates particles. So that one is also pretty self-explanatory.
And this only impacts the particles that go back and forth across the shock. And I assume not all of the particles go back and forth across the shock, just a certain percentage statistically.
Correct. About 1% of particles get promoted to cosmic rays. And exactly how that happens is still an open question and an open area of research. So the process by which particles go from being regular old ISM particles and then get injected into that process, diffusing back and forth, that's still an open area of research.
So you're a theoretical astrophysicist. You love hiking, Star Trek, puppies. You're incredibly attractive. I guess my question is, how would you describe your perfect first date?
Well, I would love a date in which the person I was talking to actually listened to what I had to say and wasn't just objectifying me.
So maybe if they asked about your research in detail?
Yes, but they would have to show genuine interest.
Okay, genuine interest. I can do that. So your recent paper was just submitted and you recently gave a plenary or 30-minute talk to the International Cosmic Ray Conference. Could you tell me a little bit about what was in that paper?
Absolutely. So I already mentioned this framework that we have for accelerating particles, diffusive shock acceleration. And one really convenient feature of diffusive shock acceleration is that it's actually predictive.
What does predictive mean?
So predictive means that this theory makes predictions about what we should observe. So one of the most important parts of being a theorist, in my opinion, is that whatever theory you come up with for how something works, it needs to be testable in some way.
It's only science if you can test the theory.
Exactly. And I mentioned our laboratories are a little bit different in astrophysics, so we are only able to observe. We aren't actually able to manipulate a supernova as much as I would like to be able to do that. However, we can still make predictions about what light we should see coming from that supernova.
So it's only science if you can observe the theory.
Exactly. And so diffusive shock acceleration is predictive. In particular, it predicts a specific distribution for the particles that you accelerate. So this is a distribution in energy. Sometimes I refer to this as a spectrum. What this means is diffusive shock acceleration says this fraction of your particles should be at these lower energies, this fraction should be at these higher energies, this fraction should be in between. We can make specific predictions about that spectrum of cosmic rays, and it just so happens that those cosmic rays, so these are mostly protons that I'm talking about here, go on to interact with other particles and produce photons or light. And light is something we can observe directly. And so the distribution of cosmic rays, of particles, specifically protons and the like, has a bearing on the distribution of photons or light that we end up seeing. And so you can think of a spectrum for photons, a photon energy distribution, as how much blue versus how much red you have. So we can use that almost as a fingerprint of sorts, and use it to see, does this observation match the prediction that was in my theory?
Was it truly Mrs. Peacock with the rope in the dining room?
Exactly.
Does it match the theory?
So that's the problem. It seems like it doesn't. It's close, but not quite there.
That's not good.
Yeah. So there's a specific spectrum that diffusive shock acceleration predicts, and what we tend to observe from actual supernova remnants is something that's a little bit steeper, where steeper in my jargon means fewer particles at high energies. So more of the particles are low energy cosmic rays, which is still, a decent amount of energy, but not the really high energy stuff. So again, steep in my jargon means fewer particles at higher energies. These observations are showing that there is this discrepancy. We have steeper spectra than the traditional theory predicts. And in fact, if you make, little modifications to try to make diffusive shock acceleration more accurate, so we call these, nonlinear corrections, if you will, these corrections actually work against you. They go in the wrong direction. So they predict more particles at high energies, which is exactly the opposite of what we are seeing in observations. And so my work is focused on addressing that discrepancy.
You're taking this theory that is predictive, predicted it wrong, and trying to make the theory predict it right and match observations.
Exactly.
So even though normally we think of theory or hypothesis, then experiment or observation, then is it right or not, you're now doing theory to observation back to theory. So you're kind of following observation a little.
A little bit, yes. That being said, this is actually a more realistic description of how science often works. So you might have learned about the scientific method in school, and it's very linear. You have this hypothesis, and that hypothesis leads to an experiment. You either prove or disprove your hypothesis, and that's the end of it. That's not quite how it works in the real world. You often have a theory, you have observations, the observations contradict the theory, you come up with a new theory, and you iterate in that manner until you think you have a good explanation for what's going on. Now, what I will say is that the solution to this problem, the steep spectra problem, actually wasn't discovered with pen and paper theory. So the solution that I talk about in this paper came from simulations. So these are basically computer simulations that are being run on supercomputers. And this is actually the closest thing we have to a laboratory in which we can actually manipulate parameters. Essentially what you're doing here is you are taking the most fundamental physics that you know, and you are just saying, okay, let's make some particles and let's let them propagate in some magnetic field that we set, and let's see what happens. And so to do this requires extremely powerful computing, which is why these simulations tend to be expensive. You can't just do them on your laptop. But this is what can sometimes lead to new discoveries and can give you access to kind of the microphysics, the small scale stuff that you can't see with observations. So we have this steep spectra problem. Funnily enough, what we found is that simulations, so big computer models, were actually producing steep spectra too. And we weren't quite sure why. Further analysis of these simulations, which kind of give us a window into the microphysics or the small scale stuff that you can't see with a telescope, for example. This analysis showed that there was something that was developing behind the shock, something that we hadn't seen before. We called it a postcursor. Like a precursor is a thing in front of the shock and a postcursor is the thing behind it. We found that there is a net drift of magnetic fluctuations, but also of particles in the downstream or the region behind the shock. And so this net drift that we discovered in simulations is responsible for altering the spectrum of cosmic rays. So diffusive shock acceleration predicts a particular spectrum or energy distribution of cosmic rays, assuming the shock hydrodynamics, so basically the flow in front of the shock and the flow behind the shock, behave a certain way. Turns out we were wrong about how those flows behaved, and that can actually affect the spectrum. In particular, we are finding that we have this drift away from the shock, behind the shock. So you can think of it as stuff, magnetic fluctuations, and particles are moving toward the center of the supernova remnant. And so that's actually moving particles away from the shock where they get accelerated, and so that means you have fewer high energy particles. And so that gives you a steeper spectrum. So my paper was actually taking that result from simulations and generalizing it. So you can't really run simulations for a bunch of different supernova remnants. It's too expensive. These things take enormous amounts of computing power. So what I have is I actually have a code that is what we call semi-analytic. It's much simpler, It makes a few more approximations, but it runs very quickly. I can do everything in my research on a laptop. And so that meant that I could take this post-cursor framework, this framework in which we have a flow moving behind the shock, and then I could generalize it to a bunch of different shocks. So we could talk about really young supernova remnants that are moving super quickly. We could talk about older, slower supernova remnants. We could talk about what if you have a shock that's expanding into a really dense medium. That affects things as well. We can generalize all of that, and then we can see when we generalize this result and we test for a lot of different supernova remnants, can we match observations of these different types of supernova remnants? And the big important thing that we find is that yes, we can. So, for example, we can predict that we would have really, really steep spectra for young supernova remnants. These are really fast shocks. The thing exploded, maybe a few days ago. These things are moving fast and they have steep spectra, and we can actually explain that with this framework. And then on the other hand, we can explain the still steep but not quite so steep spectra that you get with older, slower supernova remnants as well. And so this is the crux, is basically my research was testing this potential solution and seeing if it really does hold up to observations, and it appears that it does.
So you took a predictive theory that predicted a thing wrong, made a slight tweak, basically found a little mini effect in this overall mechanism, applied it, and all of a sudden all the predictions lined up.
Exactly. It felt really good. Except when the code broke a few times. It doesn't break anymore.
How do you think the ship's sensors in Star Trek get optical resolution so good from several light years away? Like, I'm willing to ignore all of the warp drive stuff, inertial dampeners, but sensor resolution. Like, they say magnifying on a ship that is many light years away, and they can get, down to the meter while they're also traveling at warp. Like, how does that work?
I'm glad you pointed out that issue, because it's something that no one else seems to notice or care about, but it is my little hill I like to die on. And I have come up with what I think is a clever workaround that still requires some suspension of disbelief, but hey, it's Star Trek, it's the future, there are warp drives, there's artificial gravity, there are inertial dampeners. I'm okay with it. The basic idea is that we can calculate how fine a resolution you can see, so the smallest details that you can make out, as a function of how far away you are from the thing, how big the thing is, and how big your telescope is. And we know the telescope on a starship is the deflector dish, which is 10 meters maybe.
Which is still pretty big.
Yeah, no, that's a big telescope. But 10-meter class telescopes actually exist on Earth. We've built them. So we know that these things have some limitations. They're very good. They're state of the art for us. But this is the far future. And you're definitely not going to be able to see a starship 1 light year away with that 1 meter resolution where you can make out windows on said starship with a telescope like that. So what do? My theory, or my headcanon if you will, is that, well, we have warp technology. We have the ability to mess around with things like gravity. We have the ability to warp space-time. So what if you made a gravitational lens? So for those of you who don't know, a gravitational lens is something that exists naturally in the universe, and it's basically a convenient chance alignment. So massive objects, things with large gravitational fields, actually bend space-time around them. And so that means that if you have some light that's passing by that really massive object, that light's going to get deflected. And so if you have the right alignment of thing emitting light and thing bending the light in between you, the observer, and that background source of light, you can actually create a little lens. You can magnify the background object. So my fun headcanon for Star Trek, I haven't done any of the math. I don't actually know what crazy things you'd need to do to make this work. But my headcanon is that you have an artificial gravitational lens produced by your starship using 24th century technology, because maybe you could do that.
And given that what we know about warp drive currently, with recent papers on the subject, you would need a supermassive black hole to warp space and travel faster than light. So assuming you had some sort of black hole-like object that could create a gravitational lens, if you already take warp drive for granted, isn't actually that big of a leap. So I can understand where you're coming from there.
Thank you. My bigger concern is how you deal with inertial dampeners. That's just space magic.
You mentioned that you'd never done the math. Would you maybe like to do the math sometime?
Is this your idea of a first date?
Hypothetically, if an overly enthusiastic redhead were to ask you out, would you prefer like a more subtle, cool approach? Asking for a friend who could definitely do subtle. The friend could definitely do subtle, and she has a puppy.
I'd love to see you try.
Okay, so in that case, would you like to hold the puppy for a second? Because she really likes you. I mean, look at this face. She's very cute, and she would very much like to be held by you.
I would love to hold the puppy.
Okay, and also, quick question. What do you want to get for dinner tonight?
It's a good question. I'm all dressed up for this interview, so maybe we
Ooh,
should
you
get
wanna go out?
something. Yeah, let's go out.
Somewhere fancy?
Yeah.
There's outdoor dining.
Yeah, although it's really hot out.
Yeah, ooh. Yeah, let's just order in.
Yeah.
You look so cute. I don't want you to get all sweaty.
Yeah, I don't want to get this shirt gross.
Yeah, that's fair. Astra out.
Ad Astra, to the stars, to the stars.
So, you're gorgeous, smart, funny, accomplished, well-spoken. Did I already say gorgeous? Anyway, I forgot my next question. What's it like being so amazing?
Sorry.
I'll do that again. I'm willing to ignore all of the warp drive stuff, inertial dampeners, but sensor resolution. Like, they say magnifying on a ship that is many light years away, and they can get, like, down to the meter while they're also traveling at warp. Like, how does that work?
So you know I have a rant about this. So I see what you're doing here.
Yes.
Anyway.
The friend could definitely do subtle, and she has a puppy.
I'd love to see you try.
You want to see me try subtle?
I think there's enough entertainment value in you trying subtle to make it a worthwhile first date.